Welcome to Scoli Sleep Stories. Before we begin, take a moment to get comfortable. Let the day soften around you and settle in for a calm documentary made for curious minds. If these stories help you rest, learn, or simply enjoy a quieter part of the day, please consider liking this episode and subscribing to the channel. Now, when you are ready, let us begin. Chapter 1. Entering the Quiet. Somewhere a room is growing dim. Perhaps a lamp has been switched off, and the light that remains comes only from the last pale edge of the sky beyond the window. The corners of the room soften. The sharp lines of the day, so clear and insistent only hours ago, begin to blur into gentle shapes. A book rests half open on a table. A cup cools quietly. The sounds that filled the afternoon, voices, footsteps, and the small machinery of ordinary life, have thinned into something distant and unhurried. This is the hour when the world seems to exhale, and though it may feel like an ending, like a door closing on the day, it is also a kind of beginning. As the surroundings settle into stillness, something within the body is preparing to enter a remarkably active state. We often think of sleep as an absence, a blank space, a stretch of time in which nothing happens, when the mind goes dark and the body simply stops. It is easy to imagine sleep this way, because from the outside, it can look like very little at all. A person lies quiet and still. Their breathing changes. Their eyes close. To an observer, almost nothing seems to be occurring. Yet within that quiet, a great deal is unfolding. Sleep is not an empty interval. It is an active, regulated state of the body and brain. It follows its own patterns, keeps its own kind of time, and moves through recognizable stages, hour after hour, in the dark. To understand this, it helps to consider a word scientists often use: physiology. Physiology simply means the way living bodies and their many parts function. It describes how they work, how they change, and how they maintain balance. When we speak of the physiology of sleep, we are speaking of everything the body does while it sleeps, and it does a great deal. During sleep, awareness of the surroundings is reduced. The sounds of the room may grow faint. A door closing somewhere nearby, or a car passing on a distant street, can still send signals to the sleeping brain, but responses to many such signals become weaker. The mind does not attend to them in quite the same way it would during the day. Posture changes, muscle activity shifts. The steady vigilance of waking life gently lowers its guard. None of this means that the brain has switched off. This is one of the most important things to understand about sleep. The sleeping brain remains active. Its many networks, the vast interconnected systems involved in memory, sensation, thought, and feeling, do not fall silent. Instead, their patterns change. Chemical signals rise and fall in new arrangements. Some regions become less responsive to the outside world, while other forms of internal activity continue. The brain is not resting in the sense of doing nothing, it is doing something different. There is a useful way to picture this. Imagine a large house at night. From the street, its windows have gone dark, and it appears entirely still. Yet inside, quiet systems continue their work. Warmth moves gently through the rooms. Pipes carry water. A clock ticks somewhere in the hall. The house is not abandoned. It is simply operating in another mode, one suited to the night. The sleeping body is something like that house. Outwardly quiet, it remains inwardly alive with changing activity. Sleep is also a recognizable sleep state. A sleep state is a pattern of behavior, brain activity, and bodily regulation. Ordinary sleep is internally organized, and it is normally reversible. Reversible means able to return to the previous state. A sleeping person can return to wakefulness, sometimes quickly and sometimes gradually, in response to an important sound, a touch, an internal signal, or the changing conditions of morning. This gentle reversibility is one quality that distinguishes sleep from coma and anesthesia. Those states are different in their causes, organization, and responsiveness. Sleep has rhythms of its own. It unfolds in recurring stages and naturally opens back toward waking. Nor is sleep exactly the same as simple rest. Quiet rest can be valuable, and the body may settle during it, but sleep includes physiological features that waking rest does not fully reproduce. Brainwaves change, responsiveness alters, muscle tone follows particular patterns. The body moves through non-REM and REM sleep, each with its own recognizable qualities. Sleep should not be described simply as unconsciousness either. Awareness of the external world is reduced, but mental experience may continue. Images can appear, thoughts can drift, dreams may unfold with color, movement, emotion, and narrative. A sleeping person may be quiet to the room while experiencing an entire inner landscape. It may be comforting to know that sleep, or something much like it, is not ours alone. Across the animal kingdom, in creatures of astonishing variety, researchers have observed sleep-like states. Birds settle into them. Fish enter quieter phases. Small insects show periods of reduced activity and altered responsiveness. These states differ greatly in form and duration, and scientists do not assume that every animal sleeps in precisely the human sense. Instead, they look for recurring behavioral and physiological signs. The details vary widely, yet the broad presence of sleep-like states across so many forms of life suggests that sleep answers some deep and ancient biological need. Here we arrive at something honest and quietly remarkable. Scientists do not yet have one complete explanation for why sleep evolved, or exactly how all its benefits arise. Several functions may be involved, and different aspects of sleep may support different processes. Research continues to refine the picture. What is clear is that sleep matters broadly. It is connected with attention and memory, mood and emotional regulation. It is woven into immune activity, metabolism, hormone timing, and the changing work of the heart and blood vessels. Its importance is also visible in the difficulties associated with repeatedly obtaining too little sleep, although one unusual night does not by itself define a pattern, and even from one night to the next, it is not required to look flawless. It need not be a perfectly unbroken line. Brief awakenings are common, and many are never remembered. Stages may last for different lengths of time. Dreams may be recalled vividly, faintly, or not at all. The night has structure, but it is a living structure, flexible rather than mechanical. So the room grows dim, and the day releases its hold. It may seem that nothing much will happen until the light returns, but the truth is gentler and more interesting. Night is not an empty space between 2 days. It is another mode of life. And night does not arrive all at once for the body. Long before sleep begins, an inner sense of time has already been keeping track of the changing light, the length of the day, and the slow turning toward evening. That inner timekeeper has been at work for hours, quietly preparing the way. It is there, in the body's own clock, that the story of sleep continues. Chapter 2. The Body's Inner Clock. Morning light can enter a room almost unnoticed. At first, there may be only a pale line around a curtain. Then familiar objects become distinct again. The wall takes on color. The edge of a table appears. Even through closed eyelids, changing brightness can reach the eyes and offer the body information about the world outside. Evening gives another kind of signal. Shadows lengthen, brightness fades, the colors of the sky change, and indoor light takes the place of daylight. The body does not respond to these changes with a single sudden movement. Instead, many biological processes gradually adjust their timing. These daily patterns are called circadian rhythms. The word circadian comes from Latin roots meaning about a day. Circadian rhythms repeat on a period of roughly 24 hours, though the human clock is not a perfectly fixed timer. It is adjusted each day by signals from the environment. Sleep and wakefulness are among the most familiar circadian patterns, but they are not the only ones. Alertness changes across the day. Core body temperature rises and falls. Hormones follow timed patterns. Digestion and metabolism also vary with biological time. Many parts of the body behave differently at midday than they do during the biological night. Near the center of this timing system is a small group of cells in the brain called the suprachiasmatic nucleus, usually shortened to the letters SCN. The SCN lies in the hypothalamus, a region involved in coordinating many basic bodily functions. Though small, it acts as the brain's principal circadian timekeeper. It can be imagined as a quiet conductor. Throughout the body, cells and tissues contain timing systems of their own. The liver, muscles, digestive organs, and other tissues follow daily rhythms. The SCN helps keep these many clocks loosely aligned, as a conductor might guide musicians through the same piece, while each plays a different part. The coordination is not absolute. Food timing, physical activity, and other signals can influence clocks and tissues outside the brain. These are sometimes called peripheral clocks. The whole system is less like a row of identical watches and more like a living ensemble, kept together by several overlapping cues. Light is one of the most important of those cues. Inside the retina, at the back of the eye, specialized light-sensitive cells detect environmental brightness. These cells contain a pigment called melanopsin. They send information about light toward the SCN, allowing the brain's clock to compare internal time with the changing day outside. This process of adjustment is called entrainment. Entrainment is the alignment of an internal rhythm with an outside cycle. Morning light and evening light can both help place the body clock in local time, though their effects depend on when the light arrives. The response to light cannot be reduced to one simple rule. Wavelength matters, but so do brightness, duration, timing, and previous light exposure. A softly lit evening and a brilliant morning offer different patterns of information. The circadian system interprets these signals in relation to its current phase. A person's circadian phase is simply where they are within their internal biological cycle. Biological morning does not always correspond precisely with sunrise or a number on a clock. It depends partly on the person's own timing. As dim conditions arrive during the biological evening, levels of a hormone called melatonin usually begin to rise. Melatonin is produced mainly by the pineal gland. It travels through the body as a chemical messenger and helps signal that biological night is underway. Melatonin is sometimes spoken of as if it were a switch that forces the brain into sleep. That description is too simple. It is better understood as a timing signal. Its rise announces night within the body, but it does not act alone, and it does not guarantee that sleep will begin immediately. The circadian system can support alertness even after a person has been awake for many hours. At other biological times, it can strengthen the tendency toward sleep. This is one reason sleepiness is not determined only by how long someone has been awake. Time awake matters, but biological timing matters too. People also differ in their preferred timing. This tendency is called chronotype. Some people lean naturally toward earlier sleep and earlier activity. Others tend toward later hours. Many fall somewhere between. Chronotype reflects biological influences as well as environmental and social conditions. It is not simply a matter of will or character. The clock also changes across a lifetime. A child, an adolescent, a middle-aged adult, and an older adult may experience different tendencies in sleep timing. Yet at every age, the clock remains responsive. It continues to receive the quiet messages of light and darkness, activity and meals, routine and season. Because the clock is living rather than mechanical, its rhythm is approximate. It can shift. Travel across time zones may place internal time at odds with local time. Night work can ask wakefulness to occur during biological night. Even ordinary changes in schedule can alter the alignment among sleep, light, meals, and activity. Still, beneath these variations, the basic image remains simple. Light reaches the eyes. The SCN receives the signal. Timed messages move through the brain and body. Many smaller clocks adjust their patterns. Melatonin rises in dim biological evening and falls as biological daytime returns. Alertness and sleep tendency change with the hour. The body has been reading the day all along. Yet the inner clock is only one of the two great currents that shape sleep. Circadian timing may signal that evening has arrived, but another influence has been building through every waking hour. It gathers gradually, not like a command, but like a tide. It is the gentle pressure created by time awake. Chapter 3. The Gentle Weight of Sleep Pressure. Across a waking day, small moments accumulate. There are conversations, decisions, movements, and periods of concentration. There may be long stretches of activity or quiet intervals with little to do. Yet as long as wakefulness continues, the biological tendency towards sleep generally grows. Scientists often describe this tendency with the phrase homeostatic sleep pressure. Homeostasis means regulation that helps maintain internal balance. Sleep pressure is not a literal pressure and not a substance with physical weight. It is a useful way of describing the increasing drive for sleep that usually develops during wakefulness and declines during sleep. Imagine fine grains settling into a bowl over the course of a day. No single grain changes very much, but gradually the bowl becomes fuller. Or imagine a tide moving inward so slowly that the change is difficult to notice from one minute to the next. Hours later, the shoreline looks different. Sleep pressure often feels like that. A common scientific framework known as the two-process model describes sleep timing through two interacting influences. The first is process S. The letter S refers to the homeostatic process. Process S generally rises during wakefulness and falls during sleep. The second is process C, the circadian process. Process C changes the tendency towards sleep or alertness according to biological time. These two processes do not always point in the same direction. Late in the day, sleep pressure may be strong because many hours have passed since waking. At the same time, the circadian system may still be supporting alertness. This can help explain why a person sometimes feels a temporary evening lift, even after a long day. Later, as circadian alerting signals ease and biological night becomes established, the accumulated sleep pressure and the circadian tendency towards sleep may align. Two slow currents begin to move together. Sleep then becomes more likely. One chemical involved in this regulation is adenosine. Adenosine participates in many aspects of cellular energy use. During wakefulness, it tends to accumulate in parts of the brain. It can bind to cellular structures known as receptors. A receptor is a structure that responds to a particular chemical signal, rather as a lock responds to a key of the right shape. When adenosine acts at certain receptors, it can contribute to sleepiness, but it is only one part of a much larger system. Sleepiness does not have a single chemical cause. Many network signals and timing processes work together. Caffeine illustrates the role of adenosine. Caffeine increases alertness primarily by blocking adenosine receptors. For a time, adenosine signal is less able to produce its usual effect. Yet caffeine does not instantly remove the accumulated adenosine. It changes how strongly that signal is felt while the caffeine remains active. The underlying sleep pressure may still be present. This is another reminder that alertness and sleep need not be simple opposites. A person can feel stimulated while still carrying considerable sleep pressure. They can also feel tired without being ready to fall asleep. The words sleepiness and fatigue describe related but distinct experiences. Sleepiness is the tendency or likelihood of falling asleep. Fatigue is a sense of exhaustion or reduced capacity, and it does not always lead directly to sleep. Low motivation can overlap with both, but it is not identical to either. The body's signals rarely fit into only one word. During non-REM sleep, especially deep N3 sleep, researchers can measure slow-wave activity in the brain's electrical patterns. This slow-wave activity is often stronger after extended wakefulness, when sleep pressure has built more than usual. As sleep continues, that intensity generally declines. In this way, the sleeping brain carries a trace of the day that came before. The length and nature of prior wakefulness can influence the night's architecture. Sleep is not isolated from waking life. The two-process model is valuable because it offers a clear picture of why sleep occurs when it does. One current reflects time spent awake. The other reflects biological time. Yet it remains a model, not a complete explanation for every aspect of sleep. Human sleep is influenced by environment, health, age, substances, emotion, habit, and many other conditions. No single diagram can hold all of that variation. Still, the two currents provide a calm and useful starting point. Process S rises with wakefulness and eases during sleep. Process C carries the daily message of the inner clock. At some hours they pull in different directions. At others they align. As they begin to move together, the boundary around wakefulness can soften. Attention becomes less steady. A thought begins clearly, then drifts from its path. Sounds seem to recede. Muscles loosen, though small movements may continue. The transition is rarely a sharply perceived instant. More often it is noticed only afterward. One moment belongs to waking, another belongs to sleep. Between them lies a threshold with no hard edge. Chapter 4. Crossing the Threshold. The transition from wakefulness into sleep is called sleep onset. The phrase sounds precise, as though sleep begins at one clearly marked second. Yet the experience is usually more gradual. There may be no single moment that can be felt and remembered. Awareness becomes less steady, then briefly sharpens, then drifts again. The threshold is crossed without ceremony. Thoughts begin to loosen from one another. During full wakefulness, one idea often leads deliberately to the next. Near sleep onset, That order can fade. A remembered conversation may become a place. The place may become a color, a face, or a fragment of sound. Connections appear without the careful logic of daytime thought. It can be imagined as boats drifting from a dock. While tied in place, each boat has a clear position. Once the ropes loosen, the boats move gently with the water. They remain present, but their arrangement becomes less fixed. The earliest stage of non-REM sleep is called N1. It often serves as a brief bridge between wakefulness and more established sleep. In N1, awareness of the surroundings becomes less reliable. A person may still respond fairly easily to a sound or a touch, and if awakened, they may feel that they had not yet been asleep. Meanwhile, the measurable activity of the brain begins to change. Eye movements may become slow. Muscle tone, the low level of tension normally present in muscles, generally decreases. The body grows less prepared for immediate action. This relaxation is not complete or uniform. A sleeper may adjust position, move a hand, swallow, or take a deeper breath. Small changes remain part of ordinary sleep onset. Stillness need not be perfect. Breathing and heart rate may become more regular as wakefulness recedes, though normal variation continues. The body is not following a rigid script. It is entering a state with its own flexible patterns. Brief dreamlike images and sensations can also appear near the threshold. These are known as hypnagogic experiences. Hypnagogic simply means occurring while falling asleep. A face may appear for an instant without belonging to a complete story. A voice may seem to speak a word. There may be the impression of floating, turning, or stepping onto a surface that is not really there. Some people experience a sudden sense of falling. These experiences are common, though not universal. They do not require a full dream. They can be only fragments, arriving at the border where perception, memory, and imagination become difficult to separate. A distant sound in the room may blend with an internal image. A settling wall may become a knock in a half-formed scene. The mind begins to work with less information from the outer world, and interiorly generated experience becomes more prominent. At times, a brief muscle contraction interrupts the drift. This is called a hypnic jerk, or a larger part of the body may move suddenly. The sensation can accompany an image of stumbling or falling, though it does not always do so. Hypnic jerks are common, but not everyone notices them, and they do not occur every night. They are one example of how sleep onset can contain movement as well as stillness. There may also be moments when awareness seems to return. A person shifts, notices the room again, and then drifts onward. The boundary is not a one-way gate. Wakefulness and N1 can alternate before sleep becomes more stable. From the inside, this passage is often difficult to observe. The very systems that might carefully note the moment are themselves changing. Attention softens, memory formation shifts. By the time sleep has arrived, the exact path into it may already be hard to reconstruct. From the outside, researchers can identify the transition by examining physiological signals. Brain activity recorded at the scalp changes, eye movements and muscle activity change as well. Together, these measurements allow sleep to be divided into recognizable stages. But those stages are not separate rooms with locked doors. Their boundaries are practical, scientific distinctions within a continuous biological process. One pattern blends into another. The classification helps describe what is happening without making the night more rigid than it truly is. N1 is only the first layer of quiet. As sleep continues, responsiveness to the environment usually decreases further. Distinctive bursts and waves begin to appear in the electrical activity of the brain. Body temperature continues its nighttime course. Later, broad, slow waves may become prominent. The sleeper has crossed the first threshold. Though the journey is not a straight descent, sleep can lighten again. A sound may bring awareness toward the surface. A position may change. Then the body moves onward. The room is still present. Its sounds have not vanished, yet they have moved farther from the center of attention. Thought has begun to become dreamlike, and sleep, now established, continues changing shape. Chapter 5. The Stages of Non-REM Sleep. Modern sleep scoring recognizes four main stages: N1, N2, N3, and REM sleep. The first three belong to non-REM sleep. The name simply means sleep without the defining features of rapid eye movement sleep. Each non-REM stage has characteristic patterns, but none is a sealed compartment. Sleep shifts between them with soft, changing boundaries. Researchers identify the stages using several measurements. An electroencephalogram, or EEG, records electrical activity measured at the scalp. Additional sensors record eye movements and muscle activity. Together, these signals reveal patterns that cannot be seen merely by watching someone sleep. N1 is the lightest non-REM stage. It often appears near sleep onset and may last only briefly. Slow eye movements can occur. Muscle tone decreases. Brain activity begins moving away from waking patterns. A person in N1 may still respond rather easily to the environment. A sound can bring attention back to the room, and the person may report that they were only thinking, even though the recording has begun to show sleep. N1 is a bridge. It may be crossed once, or revisited as sleep grows lighter during the night. As sleep becomes more established, N2 appears. N2 usually occupies the largest portion of adult sleep. Responsiveness to the environment lessens further, and body temperature continues its nighttime decline. The EEG displays two especially recognizable events during N2. The first is the sleep spindle. A spindle is a short burst of rhythmic activity, rising and fading over a brief interval. It can be pictured as a small ripple moving across a quiet lake, distinct for a moment, then gone. Sleep spindles are associated with the regulation of sensory information and with aspects of learning and memory processing. Their exact roles are still being studied. They are not signs that the brain has awakened. They are part of the organized activity of sleep. The second characteristic event is the K-complex. A K-complex is a large, distinct wave. It may occur spontaneously, or it may follow a sound or another outside signal. The sleeping brain has not become deaf to the world. It can continue registering some events without producing full awakening. A K-complex may be one sign of this changing relationship with the environment, though its functions are broader and not captured by one explanation. N2 can therefore feel quiet from the outside, while containing rich patterned activity within. Spindles appear and disappear. K-complexes rise like solitary waves. The brain remains active, but in a form unlike ordinary waking thought. From N2, sleep may deepen into N3. N3 is often called slow-wave sleep, because of its prominent low-frequency EEG activity. It is also commonly called deep non-REM sleep. The waves measured at the scalp are broad and high in amplitude, moving more slowly than many patterns seen during wakefulness or REM. Deep sleep does not mean inactive sleep. The brain is still functioning, and the body continues breathing, circulating blood, regulating temperature, and responding selectively to internal and external conditions. The word deep refers to the stage's physiological pattern, and in part to reduced responsiveness. A stronger stimulus may be needed to awaken someone from N3, although awakening thresholds vary. A meaningful sound can matter more than a louder but unimportant one. The sleeping brain continues to evaluate the world in limited and changing ways. N3 is generally more concentrated in the first portion of a typical night. This is when sleep pressure is often strongest. The slow waves may be especially prominent after a longer period of wakefulness. Growth hormone is released in pulses, and a major pulse is often associated with early night slow-wave sleep, particularly in younger people. This relationship is one part of the body's nighttime coordination. It does not mean that all growth, repair, or tissue maintenance occurs only in N3. Such processes also continue at other times, including during wakefulness. The amount of N3 varies. Age makes a difference. So do individual biology, prior sleep, health, timing, and the particular night. Children often have prominent deep sleep. In many adults, the amount gradually decreases with age. Some older descriptions of sleep refer to 4 non-REM stages, or 5 stages in total. That difference comes from an earlier classification system, which divided deep sleep into stages 3 and 4. Current clinical scoring combines those older deep stages into N3. The biology did not suddenly change when the naming system changed. The categories are tools, refined as scientists seek consistent ways to describe a fluid process. Across N1, N2, and N3, the night seems to deepen, though not like a staircase descended one step at a time. A sleeper can move forward and back. N3 may give way to N2. A brief awakening may occur. Another stage may follow. It is better to imagine layers of quiet shifting over one another. N1 is the first softening of awareness. N2 brings greater separation from the surroundings, along with spindles and K-complexes. N3 carries broad, slow waves and is usually most abundant earlier in the sleep period. Then at intervals, sleep changes in another direction. The slow waves recede. Brain activity becomes mixed and faster in some regions. The eyes may begin moving lightly beneath closed lids. Most skeletal muscles become remarkably still. The sleeper is entering REM. Chapter 6. The dreaming state of REM. REM means rapid eye movement sleep. The name comes from one of its most visible signs. During this stage, the eyes often move quickly beneath closed eyelids. These movements may occur in clusters and then pause. They are part of a distinct physiological state that differs both from wakefulness and from non-REM sleep. Brain activity during REM is mixed and relatively fast in some regions. Certain features resemble waking activity, but REM is not simply wakefulness with closed eyes. Its chemistry, patterns of connectivity, sensory input, and control of the muscles are different. The brain remains within sleep. REM is strongly associated with vivid dreaming. When people are awakened from REM, they often report experiences with imagery, emotion, motion, and narrative. A familiar place may be rearranged. A conversation may unfold in a location that could never exist. Time may stretch or collapse without causing surprise. Yet dreaming is not exclusive to REM. Dreams and thought-like experiences can occur during non-REM sleep as well. On average, non-REM reports may be shorter or less vivid, but there is considerable overlap. REM is a measurable biological state. Dreaming is a subjective mental experience. The two are closely related, but they are not the same thing. One of REM sleep's most striking features is the marked reduction of most skeletal muscle activity. Brainstem systems send signals that strongly suppress normal muscle tone. This temporary muscle stillness is known as REM atonia. Atonia means a strong reduction in muscle tone. It need not be imagined as complete or alarming stillness. The muscles that move the eyes remain active. Breathing muscles continue their essential work. Small twitches can appear in the face or limbs. The heart continues beating. Breathing continues automatically. Both may become less regular during REM than during stable non-REM sleep. The body is quiet in some ways and variable in others. REM atonia is generated through systems in the brainstem, the lower portion of the brain that connects with the spinal cord. It is one part of the organized physiology of REM, just as slow waves are part of N3 and spindles are part of N2. Within the brain, activity does not follow the tidy logic of the waking world. Sensory input from the room is reduced. Internally generated signals can take a larger role. Memory fragments, feelings, images, and expectations may combine into scenes. A face from years ago may appear in a recently visited room. A road may become a corridor. A familiar voice may belong to no visible speaker. The dreaming mind can accept these changes without pausing to explain them. Not every REM period gives rise to a remembered dream. A dream may occur and leave no lasting memory, or the experience may be only faintly recalled. Dream recall depends partly on whether awakening occurs during or soon after the dream, and whether attention turns toward it before waking thoughts interfere. REM periods also change across a typical night. Early REM periods are often shorter. Later ones tend to become longer, especially toward biological morning. This is one reason vivid dreams are often remembered near the end of sleep, although dreams may arise at other times as well. REM does not appear only once. It returns repeatedly, woven among the non-REM stages. Nor does every return look identical. One REM period may be brief, another longer. Physiological activity varies from minute to minute. The sleeping body can move out of REM into lighter non-REM sleep or toward a brief awakening. It may shift position once muscle tone returns, then enter another cycle. Many such transitions leave no memory. From the outside, the sleeper may seem almost unchanged. The room remains quiet. Breathing continues. The eyelids are closed. Yet within, the nature of sleep has altered profoundly. The broad, slow waves of deep non-REM sleep have given way to faster mixed activity. The eyes move lightly. The muscles remain mostly still. Images gather and transform. Then REM recedes, and another pattern begins. Across the night, these states return like waves reaching a shoreline. Each follows a broad rhythm, but no two are exactly alike. Some descend more deeply into N3, some carry longer periods of REM. Some are interrupted by a moment near the surface. Together, these patterns form the architecture of sleep. Chapter 7. The Architecture of a Night. Architecture usually brings to mind something solid: walls, windows, arches, and carefully measured rooms. Sleep architecture is less rigid. It means the pattern and timing of sleep stages across a sleep period. The word helps describe the night's organization, but the structure itself remains fluid. Sleep is built from changing states rather than stone. In a typical sleep period, non-REM and REM recur in cycles. Sleep may begin with N1, move into N2, deepen into N3, return toward lighter sleep, and then enter REM. Yet this is only a broad pattern. Real sleep does not always follow one flawless sequence. A sleeper may move from N2 to N3, then return to N2. A brief awakening may appear before REM. One stage may be short, another prolonged. The night has order, but not mechanical perfection. Sleep cycles are often casually described as lasting 90 minutes. 90 minutes is a convenient average, not a rule. Adult cycles often fall within a broad range of about 70 to 120 minutes, and their lengths vary both between people and within the same night. There is no fixed number of cycles that everyone must complete. The shape of sleep depends on the length of the sleep period and on many other influences. Early cycles generally contain more N3 or slow wave sleep. At that point, homeostatic sleep pressure is still relatively strong. The broad, slow waves of deep non-REM sleep are therefore more concentrated in the earlier part of the night. As sleep continues, pressure gradually declines. Later cycles usually contain less N3 and more REM. Lighter non-REM sleep also becomes more common toward morning. The night can be imagined as a coastline visited by several waves. The first waves may move deeply over the shore, carrying long stretches of slow wave sleep. Later waves may be shallower, but filled with longer REM periods and more shifting imagery. Each wave returns to familiar ground, though each has a slightly different shape. At the edges of these cycles, brief awakenings are common. A sleeper may rise toward the surface for only a few seconds. The body may change position. The room may be registered for a moment. Then sleep resumes. Many of these brief awakenings are not remembered. Memory does not reliably preserve every transition. By morning, sleep can seem continuous, even when the brain moved toward wakefulness several times. Waking during the night does not automatically mean that sleep has failed. Normal sleep is not a perfectly unbroken state. What matters in research and health is often the broader pattern over time, not one isolated movement or awakening. Sleep architecture can change for many reasons. Age influences the amount and distribution of different stages. Prior sleep affects sleep pressure. Circadian timing alters when sleep is occurring relative to internal biological night. Illness, medications, other substances, and the sleeping environment can also change the pattern. Noise, temperature, unfamiliar surroundings, or interruptions may shape a particular night. One night's architecture does not necessarily represent another. Researchers study sleep architecture with polysomnography. This is a laboratory or clinical sleep recording that measures brain waves, eye movements, muscle activity, breathing, and other physiological signals. These measurements allow trained specialists to identify sleep stages according to established criteria. Consumer sleep trackers work differently. A watch, ring, or bedside device may use movement, pulse, and other indirect signals to estimate when sleep occurred and which stages may have been present. Such estimates can be useful for showing broad patterns, but they are not equivalent to clinical polysomnography. No device can turn a naturally variable night into a perfect schedule. The stages themselves also do not have one single purpose each. N3 is associated with some forms of memory and hormonal activity. Spindles in N2 are linked with learning. REM may contribute to emotional and procedural processes. But the functions overlap, and sleep works as a coordinated whole. The brain does not enter one stage to perform one task, complete it, and then move to the next. Biology is more intertwined than that. Across the cycles, internal and external information continues to be managed. Sounds may be registered without awakening. Memories may be reactivated. Hormones follow their rhythms. Temperature changes. Breathing and cardiovascular activity shift with the stage. The sleeper passes through layers of quiet, imagery, slow waves, brief surfaces, and deeper returns. By the later part of the sleep period, REM periods are often longer. Awakenings become more likely. Yet before morning arrives, much has occurred within these repeating patterns. The sleeping brain has not merely waited in darkness. It has changed its activity again and again. It has moved among distinct physiological states, while processes related to learning, memory, attention, emotion, and maintenance have continued. Like a library after closing, the sleeping brain remains closed to most visitors, yet far from empty. Chapter 8. The Sleeping Brain at Work. A quiet library at night may appear motionless. The chairs are empty, the lights are low, no footsteps pass between the shelves, yet the books remain connected by subject, history, and meaning. A new volume belongs somewhere within that larger arrangement, even if its place is not immediately clear. Memory can be imagined in a similar way, though the brain does not consciously sort experience as a librarian would. New memories begin forming while we are awake. Attention, experience, and rehearsal all matter. Sleep does not create every memory, nor does it preserve every detail, but sleep supports several forms of memory consolidation. Memory consolidation is the process through which newly acquired information becomes more stable or more fully integrated with existing knowledge. It can involve strengthening parts of a memory, reorganizing relationships among memories, and changing how information can later be accessed. Different sleep features are associated with different kinds of learning. Slow-wave sleep is linked with aspects of factual and event memory. These include knowledge and experiences that can often be described consciously. During sleep, patterns connected with recent learning may be reactivated and altered. Sleep spindles, the brief rhythmic bursts seen especially in N2, are also associated with memory processing. Studies link their activity with learning, though their roles are still being investigated. REM may contribute to some forms of procedural learning, such as learning skills and sequences, and to aspects of emotional memory. Yet it would be too simple to say that REM processes all emotion or completes all learning. Emotional brain networks function differently during sleep, but their work is distributed across states and remains an active field of research. Sleep may help connect recent information with older knowledge. A new experience does not remain isolated. Over time, it can become part of a wider network of associations. Imagine a path across grass. One crossing leaves a faint trace. Repeated use makes the route more familiar. Neural change is far more complex than a path, but the image captures something gentle. Patterns can become easier to follow through repeated activation and adjustment. A neural connection is a functional link between nerve cells. A synapse is a junction through which one nerve cell influences another. Learning changes activity across many such connections. One influential idea, called the synaptic homeostasis hypothesis, proposes that sleep helps recalibrate the strength of neural connections after the widespread changes of waking experience. Some connections may be maintained or strengthened, while overall activity is adjusted. This hypothesis has shaped research, but is not a complete or settled explanation of sleep. Science often advances through such carefully tested proposals. Uncertainty is not emptiness. It is a boundary around what the evidence can presently support. Sleep also affects how the waking brain functions afterward. Attention and decision-making are associated with sleep history. When sleep is repeatedly insufficient, concentration and judgment may become less reliable. Yet a single unusual night should not be treated as a complete measure of a person's health or ability. Patterns over time are more informative. Another area of research concerns fluid movement through and around brain tissue. The brain produces metabolic waste as a natural result of cellular activity. Animal studies strongly support the idea that sleep is associated with changes in fluid transport and waste clearance. A proposed pathway involved in this movement is sometimes called the glymphatic system. The name refers to a network through which fluid may move through fine spaces around brain cells. It can be pictured as a slow current moving through narrow channels, but the image must remain cautious. Saying that sleep washes away all toxins would go beyond the evidence. How findings from animal studies translate to ordinary human sleep is still being investigated. The sleeping brain is not being scrubbed clean or returned to a perfect beginning. It is a living organ in continuous activity, influenced by both sleep and wakefulness. Memory consolidation also does not occur only during sleep. Waking attention, practice, reflection, and repeated experience all help learning. Sleep appears to support these processes rather than replacing them, nor does the brain decide with conscious purpose which memories deserve to remain. Some details fade, others become stable. Emotional significance, repetition, prior knowledge, and later experience can all influence what is retained. The image of books returning to shelves can still be useful, provided the shelves are imagined as flexible. Each new book can alter the meaning of those already there. Categories overlap. Some volumes remain easy to find, while others slowly become faint. Through N2 spindles, slow wave activity, REM, and the transitions among them, the brain's patterns continue to change. Outside, the room remains quiet. Within, signals move through networks. Memories are revisited and reorganized. Fluid movement changes. Connections are adjusted. None of this supplies one final answer to why sleep exists, but together these processes reveal sleep as active and deeply integrated with waking life. And the brain does not work alone. It rests within a body whose temperature is falling, whose hormones are following timed rhythms, and whose heart and breathing continue through every stage. The whole body shares the night. Chapter 9. The Resting and Repairing Body. Beneath a blanket, warmth gathers near the skin, while the body's inner temperature follows its nighttime rhythm. Core body temperature, the temperature of the internal tissues and organs, typically falls during the biological night. It usually reaches a low point in the latter portion of the sleep period. This change begins as part of circadian timing and is not caused by sleep alone. The skin may remain comfortably warm even while heat leaves the core. The body is not becoming cold in a simple sense. It is redistributing and regulating temperature according to a daily pattern. Many other systems change their activity as sleep unfolds. Heart rate and blood pressure often decrease during non-REM sleep. This can be described as a period of cardiovascular rest, provided the phrase is understood broadly. The heart never stops working. Blood continues to circulate through every tissue. During REM, heart rate and blood pressure can become more variable. Breathing may also be less regular than it is during stable non-REM sleep. Across all stages, breathing continues automatically, adjusted by systems that respond to the body's needs. A slower rhythm, then greater variation. Quiet continuity, rather than stillness. Hormones also follow changing patterns. A hormone is a chemical messenger carried through the body. Some hormones are closely tied to circadian timing. Others are influenced by sleep stage, meals, activity, stress, age, and many additional conditions. Growth hormone is often released in pulses, with a major pulse associated with early night slow-wave sleep in many people, especially when they are younger. Growth hormone is involved in growth and metabolism, among other functions. This association does not mean that the body performs all repair during deep sleep. Tissue maintenance and protein building processes continue during sleep, but repair also occurs while awake. The living body is always maintaining itself. Cortisol follows another rhythm. It is generally lower around the early biological night and rises toward morning. Its pattern varies with timing and circumstances. Cortisol is not the sole cause of awakening, though its circadian rise is part of the body's preparation for biological daytime. Hormonal signals do not all arrive together. They rise and fall like quiet messages delivered at different hours. Sleep also coordinates with the immune system. The immune system consists of cells, tissues, and signaling molecules involved in defending and maintaining the body. Sleep can influence immune signaling, and immune activity can influence sleep in return. The relationship moves in both directions. During illness, immune signals can change sleepiness and sleep structure. Sleep patterns, considered over time, can also be associated with aspects of immune function. But sleep alone does not guarantee immunity, and no single night determines the whole system. Metabolism continues through the night as well. Metabolism means the chemical processes that use and transform energy and materials. The sleeping body still requires energy. The brain remains active. The lungs move. The heart pumps. Cells carry out countless reactions. Sleep is connected with appetite regulation, glucose control, and energy metabolism, particularly when patterns are examined across time. These relationships are complex. They are shaped by activity, food, health, biology, and environment as well as sleep. The body does not divide its tasks neatly into those performed by day and those performed by night. Instead, the balance changes. During waking, movement and attention are directed more strongly toward the outside world. During sleep, sensory responsiveness decreases, and physiological systems enter other patterns. Maintenance continues in both states, but its timing and emphasis can differ. The word repair can therefore be used gently, without suggesting that sleep mends everything by morning. Sleep supports conditions associated with tissue maintenance, immune coordination, hormonal timing, and metabolic regulation. It participates in the body's care rather than completing that care alone. Throughout the night, the heart continues its quiet work. Blood moves through arteries and veins, oxygen crosses from the lungs, carbon dioxide returns to be released. Temperature drifts toward its low point. Hormones arrive in pulses. Immune signals move between cells. In non-REM sleep, some rhythms become steadier. In REM, variability returns. Then another transition follows. The body is resting but not inactive. The brain is sleeping but not silent. And within this coordinated state, the mind may still create experiences of its own. A place appears, a voice speaks, a familiar face enters an unfamiliar room. Memory and imagination meet without needing to explain themselves. Chapter 10. Dreams, Stories, and Quiet Images. A dream may begin in a room that seems familiar. The window is in the right place, but beyond it lies a landscape that has never been there. A person enters, carrying the face of someone known long ago. The scene changes without transition. A hallway becomes a road becomes water. None of this may seem strange until waking. Dreams are internally generated experiences. They can include imagery, thought, emotion, sensation, and narrative. Some unfold like stories. Others are brief impressions, without a clear beginning or ending. Vivid dreams are frequently associated with REM sleep. Awakenings from REM often produce reports filled with movement, color, emotion, and unusual events. Yet dreams are not confined to REM. Non-REM sleep can also contain imagery and thought-like experience. On average, non-REM dreams may be shorter or less elaborate, but the boundary is not absolute. A vivid dream can occur outside REM, and a REM period may leave only a faint impression or no remembered experience at all. Dream content often draws upon fragments of waking life. A recent conversation may appear in altered form. An old memory may combine with a new concern. A place may carry details from several different places. Imagined material enters as well. Dreams rarely replay experience exactly. They are not direct recordings of memory. They are constructions created by a sleeping brain whose sensory input, chemistry, and network activity differ from those of wakefulness. There is no single accepted scientific theory explaining why people dream. One proposal treats dreams as byproducts of sleeping brain activity. According to this broad view, the brain generates signals, and the mind forms an experience from them. Other theories suggest that dreams may participate in memory or emotional processing. As memories are reactivated and reorganized, fragments may become part of dream experience. Still, other ideas describe dreams as simulations or predictive constructions. The brain regularly builds internal models of the world while awake, and dreaming may reflect that constructive ability continuing under the unusual conditions of sleep. These proposals are not necessarily complete opposites. More than one process may contribute, and different dreams may arise under different conditions. Research has not settled the overall function of dreaming. It is therefore too strong to say that every dream contains a hidden symbolic message. A dream about a house does not have one universal meaning. Personal associations may matter to the dreamer, but science does not provide a fixed dictionary that translates each image. It is also too strong to say that dreams are meaningless. Their relationship to memory, emotion, and brain activity remains an important subject of study. The most accurate position is one of curiosity without certainty. Dreams are not reliable predictions, nor are they flawless revelations of buried truth. They are experiences formed within sleep, influenced by the past, the present, imagination, and the changing physiology of the brain. Dream memories are often fragile. On waking, a dream may feel vivid enough to last all day. A few moments later, it begins to fade. The room remains, but the reason for being there is lost. A face lingers without a name. Then even the image dissolves. Dream recall is more likely when awakening occurs during or soon after a dream. Attention also matters. If waking thoughts immediately turn toward the time, the room, or the day ahead, the dream may disappear before it is firmly encoded as a waking memory. Encoding is the initial formation of a memory. The neurochemical conditions of sleep may not support lasting encoding in the same way as alert wakefulness. Weak encoding, rapid interference after waking, and the distinctive chemistry of sleep may all contribute to dream forgetting. No single explanation accounts for every forgotten dream. Brief awakenings during the night may sometimes preserve a fragment. Other dreams vanish entirely. By morning, a person may believe that no dreaming occurred, when the more cautious conclusion is only that no dream was recalled. The dream fades like mist when attention turns elsewhere. A landscape loses its edges. A voice becomes silence. The inner story returns to the state from which it came. Dreams differ from night to night, just as sleep itself changes across time. The sleep of a newborn is not arranged like the sleep of an adult. A child's deep sleep differs from the lighter, earlier sleep often found in older age. Across a lifetime, sleep changes shape while remaining part of the same ancient rhythm. Chapter 11. Sleep across a lifetime. Sleep changes across life, as daylight changes across the seasons. The need for sleep remains, but its timing, duration, and architecture take different forms. No age owns the ideal version. Each stage of development brings its own pattern. A newborn does not usually gather sleep into one long nighttime period. Sleep is distributed across day and night, arriving in many episodes. Circadian timing is still developing, and the distinction between biological day and night is not yet organized in a mature way. Infants spend more total time asleep than adults. They also have a larger proportion of active sleep, an infant state that shares features with adult REM. It is not identical to mature REM because the nervous system and sleep architecture are still developing. An infant may move, twitch, change facial expression, or breathe irregularly during active sleep. These patterns belong to an early stage of development rather than a smaller copy of adult sleep. As childhood continues, sleep gradually becomes more consolidated at night. Consolidated sleep means sleep gathered into one relatively continuous period. Daytime sleep often becomes less prominent, while the nighttime interval lengthens. Deep N3 sleep is often especially prominent in children. The early portion of the night may contain strong slow-wave activity. Growth, learning, circadian development, and sleep pressure all take place within a changing body. During puberty, circadian timing commonly shifts later. Biological signals that support sleep may occur later in the evening, and the tendency toward morning alertness may also move later. This does not mean every adolescent follows the same schedule, or that biology acts alone. Social routines, evening activity, light exposure, school timing, and individual differences all interact. Still, the later circadian tendency is a well-established developmental pattern. Social schedules may ask for wakefulness at times that conflict with this shift. An early clock time can arrive while the body remains closer to biological night. In adulthood, sleep timing and duration continue to vary considerably. Public health guidance commonly describes roughly 7 to 9 hours of sleep for many adults. This is a population guideline, not a precise prescription for every person. Individual needs and circumstances differ. The amount of sleep a person obtains can vary with health, responsibilities, environment, biology, and opportunity. Sleep quality and timing also matter, and no single number captures the entire experience. Across adulthood, chronotype remains diverse. Some people lean early, some late, and many change over time. A schedule that suits one person may not describe another. With older age, sleep often becomes lighter or more fragmented. N3 sleep commonly decreases, brief awakenings may become more frequent, though this is not inevitable for every person. Sleep timing also often shifts earlier. Evening sleepiness may arrive sooner, and morning waking may occur earlier. Daytime naps can become more common. Older adults do not necessarily need dramatically less sleep. The ability to obtain one long, consolidated period may change more than the underlying need. Health, pain, medications, environment, and daily routine can all influence the pattern. At every age, sleep architecture remains responsive to circumstances. Illness may alter stages. A new environment can produce a different night. Medications and other substances can change timing or continuity. Prior sleep affects the pressure carried into the next sleep period. There is continuity beneath all this change. The infant moves through many short rests across light and darkness. The child enters deep early night sleep. The adolescence clock may lean later. Adult sleep finds many forms around work, family, biology, and environment. Older sleep may arrive earlier and in lighter sections. None of these patterns is a moral measure. Sleep is not evidence of diligence or laziness. It is biology living within a social world. Across a lifetime, the two main currents remain. Sleep pressure grows during wakefulness and declines during sleep. Circadian timing helps place sleep and alertness within the day. Their balance changes with development, but their quiet interaction continues. Each night is shaped by all the nights and days that came before it, yet no single night tells the entire story. And whatever form sleep takes, it eventually loosens. Sleep pressure has eased. Later cycles carry more REM and lighter non-REM sleep. The circadian system begins to support wakefulness again. Somewhere beyond the room, darkness is becoming pale at the edges. Biological morning is approaching. Chapter 12. Returning toward morning. Morning does not always begin with sunlight. Biological morning depends on circadian phase, the current timing of a person's internal rhythm. It may arrive before dawn, after sunrise, or at another clock time entirely. Yet whenever it comes, the transition toward wakefulness is usually a process, rather than an instant. By the later portion of a typical sleep period, homeostatic sleep pressure has declined. Process S, which rose through waking hours, has eased during sleep. At the same time, Process C is changing. Circadian systems increasingly support wakefulness as biological morning approaches. The two currents that helped guide the body into sleep have shifted again. Later sleep usually contains more REM and lighter non-REM sleep than the early part of the night. Deep N3 sleep is often less prominent. Because sleep is lighter and transitions are more frequent, awakening becomes more likely. The final awakening may feel like the only one, though brief awakenings may have occurred throughout the night. Some lasted only moments. Some allowed a position change or a passing awareness of the room. Most were not stored as lasting memories. The night was never required to be a single unbroken line. Core body temperature, having reached its nighttime low, begins to rise as biological morning approaches. The change is gradual. The body is moving toward the conditions of daytime activity. Cortisol also follows its circadian rise toward morning. It contributes to the larger pattern of biological preparation, but it is not the sole cause of waking. In many people, another rise in cortisol occurs during the period shortly after awakening. This is called the cortisol awakening response. It is related to but distinct from the circadian increase that begins before waking. No single hormone opens the door to consciousness. The brain's connection with the surroundings becomes steadier. Sounds that passed unnoticed begin to separate from the background. Air moves through a vent, a floor settles, a distant vehicle crosses a street. Perhaps birds are audible, or perhaps the world outside remains dark and quiet. Closed eyelids register changing brightness. After waking, light reaching the eyes helps reinforce circadian alignment. Signals from specialized retinal cells travel toward the SCN. Melatonin is suppressed as biological daytime becomes established. Again, light does not act as one abrupt switch. Brightness, timing, duration, and circadian phase all influence the response. Wakefulness may return in layers. First there is awareness without orientation, then the room becomes familiar. The body's position is recognized. The recent dream, if there was one, may linger for a few seconds. Thought gathers itself. Memory reconnects the present moment with the day beyond it. Sometimes this return carries grogginess. The temporary reduction in alertness and performance after waking is called sleep inertia. It may be stronger after waking from deeper sleep, or after waking at an unusual biological time. Its strength and duration vary. Sleep inertia is another reminder that waking is not always an instantaneous switch. The sleeping brain does not move at once, from one complete state into another. Its networks gradually resume the patterns of alert wakefulness. A dream can still hover near the edge. A sound may seem briefly connected to it. Then external details become more stable, and the inner scene dissolves. The stages of the night are now mostly beyond memory. N1 formed the first bridge from waking. N2 brought spindles and K-complexes, brief patterns within the quiet electrical activity of sleep. N3 carried broad, slow waves, especially in the earlier cycles. REM returned with mixed brain activity, moving eyes, temporary muscle stillness, and often vivid internal experience. These states repeated in cycles, not in identical 90-minute units, but in flexible periods that often ranged broadly from 70 to 120 minutes in adults. Early cycles tended to contain more deep sleep. Later ones carried more REM and lighter non-REM sleep. Between them came small transitions, movements, and perhaps awakenings too brief to remember. Throughout it all, the brain remained active. Networks changed their patterns. Memory processes continued. Emotional systems entered different configurations. Fluid movement through and around brain tissue changed, though the meaning of these changes in normal human sleep is still being studied. The body remained active as well. Breathing continued. The heart circulated blood. Temperature followed its nighttime curve. Hormones arrived in timed pulses. Immune and metabolic signals moved through their ongoing relationships. Sleep did not shut the body down. It changed the way the body was organized. Nor did it provide one simple task with one simple result. Sleep supports attention, memory, mood, immune activity, metabolism, hormone timing, and cardiovascular regulation. Yet scientists do not have one final explanation for why sleep evolved or how every benefit arises. Much is understood. Much remains open. This balance between knowledge and mystery is part of the story. We know that an inner clock receives information about light and helps coordinate daily rhythms. We know that sleep pressure generally builds during wakefulness and declines during sleep. We can measure brain waves, eye movements, muscle activity, breathing, and heart rhythms. We can identify non-REM and REM sleep and observe their changing architecture. We can study sleep across infancy, childhood, adolescence, adulthood, and older age. We can see that its duration, timing, and stages vary across people and across nights. And still, sleep retains quiet questions. Darkness becomes charcoal gray, then pale around the edges. Or perhaps biological morning arrives beneath a night sky, according to a schedule shaped by another life and another clock. The room becomes distinct again. The mind reopens its connection with the surroundings. Sleep pressure has lessened. Circadian alerting signals are rising. Wakefulness gathers gradually, carrying forward traces of the night, whether remembered or not. Later, sleep pressure will begin to build again. Light will change. Clocks throughout the body will continue their measured rhythms. Evening, whenever it comes, will send its signals, and sleep will return, not as an empty interval, but as a living state, organized, variable, reversible, and active. A rhythm understood in many ways, yet still unfinished. Moving from waking into quiet, moving through waves, images, stillness, and change, and eventually, in its own time, moving back toward the light.